Welcome to a technical tea break. Today's talk is about refractive index and its relevance in light microscopy. I plan to discuss the following topics. What is refractive index? How does refractive index affect resolution? How refractive index affects your choice about objective lens and mounting media. So, what is refractive index? The refractive index of a material describes how fast light travels through the material. An increasing refractive index corresponds to decreasing speed of light in the material. Refractive index is defined as N equals C over V, where C is the speed of light in a vacuum and V is the phase velocity of light in the medium. For example, the refractive index of water is approximately 1.33, meaning that light travels 1.33 times as fast in vacuum as in water. The refractive index of a material determines how much the path of light is bent or refracted when entering a material. This is described by Snell's law of refraction, as shown here, where θ1 and θ2 are the angles of incidence and refraction, respectively, of a ray crossing the interface between two media with refractive indices N1 and N2. When light enters a material with a higher refractive index, the angle of refraction, θ2 in the diagram, will be smaller than the angle of incidence, θ1 in the diagram, and vice versa. So in the example on the left, the refractive index N2 is higher than the refractive index N1, and this could be an example of light crossing the interface between air and water. Refraction is the reason that a convex lens can focus light. Perpendicular light enters by the flat surface of the lens, but as it leaves the curved surface, refraction happens by different degrees because of the curvature, and light is focused to a point. But we should also be thinking about surfaces that will refract light once it leaves the objective. That means we need to think about the refractive index of the space between the lens and the sample, and also the refractive index of the sample itself. Otherwise, we're going to get interesting but unwanted effects, like a bent straw. Firstly, we're going to consider the refractive index of objective immersion media, and what that means for our imaging experiments. Thinking about refractive index, we can consider why and when we use oil or water immersion objectives rather than air objectives. So first we'll consider an air immersion objective. Light emitted by the sample passes from glass to air to glass. Refraction happens at two surfaces and both light and resolution are lost. Both the front lens of an objective and the cover slip are made of glass and have a refractive index of 1.51. The air in between them has a refractive index of approximately 1. If there is air between the cover slip and the front lens of the objective, the amount of light that gets into the objective will be limited by refraction at the air-glass interfaces, as shown by the red lines representing light rays on the diagram. Low magnification objectives are usually air immersion. As you increase the refractive index of the space between the objective lens and the cover slip, more light enters the objective front lens, and the resolvable frequencies increase too. For the oil immersion objective shown here, the oil has the same refractive index as the glass. By reducing the amount of refraction happening in the system, you're effectively maximizing the amount of light that can enter the front lens. Higher magnification objectives are usually immersion lenses. If you're unfamiliar with the concept that the angle of light entering an objective affects its resolution, we should look at the Abbe equation. Ernst Abbe described the diffraction limited resolution of a microscope by this equation. Resolvable feature size D equals lambda over 2 n sine alpha. Lambda is the wavelength of light used, n is the refractive index of the objective immersion media, alpha is the half angle of acceptance of the objective lens as shown in the previous slide. From this equation, we can see that as the angle of acceptance of the objective gets larger, as this gets larger, the resolvable feature size gets smaller. Abbe defined the ensign alpha as the numerical aperture of an objective. So the equation becomes resolvable feature size D equals lambda over 2 NA. Perhaps counterintuitively, therefore, it's not the magnification of an objective lens that gives you information about its resolution capabilities, but the numerical aperture. It's the numerical aperture, shown here as NA, that gives you information about the angle of light that can enter the objective lens, and therefore the resolution. The larger the angle of acceptance, the better the theoretical resolution. In the examples shown on this slide, both objectives are 63x magnification, but the numerical aperture values shown on the barrel, outlined in magenta, are very different. If we put numbers into the Abbe equation, using 500 nanometers as the wavelength of light, the resolvable feature size D of the air objective with an NA of 0.75 is approximately 350 nanometers, whereas the resolvable feature size D of the oil objective with a numerical aperture of 1.4 is 180 nanometers. So you might wonder why we don't always choose an oil immersion objective. After all, they will have highest NA and therefore will give the best theoretical resolution. Well, aside from the practical considerations of needing to use oil between the objective lens and the cover slip, these diagrams are based on imaging something that is right at the surface of the cover slip, shown here by the black dot. We've only taken into account the refractive index of the objective immersion media. What happens if you're imaging into the specimen? We now need to take into account the refractive index of the specimen. If the specimen, which includes the sample and the surrounding mounting media, is at a uniform refractive index different from the objective immersion media, the imaging will suffer from spherical aberration. The aberrations will be worse the further from the cover slip you image, and the bigger the refractive index difference. The example here is a specimen with a refractive index of 1.47, that of glycerol-based mounting media. If you would like a simple resource to understand spherical aberration and its effects, I recommend going to the Scientific Volume Imaging website as a good source of information. The diagrams on this slide are taken from that site. Spherical aberration is an optical effect occurring when the oblique rays entering a lens are focused in a different location than the central rays. In microscopy, the main cause of spherical aberration is mismatch between the refractive index of the lens immersion medium and the specimen embedding medium. For example, the lower diagram shown here. On the left side, an XZ view of the point spread function of a water immersion objective. On the right side, the same objective, imaging 10 microns into glycerol, now has a much broader point spread function. The signal has been effectively blurred by spherical aberration. If the mismatch is large, as in this example, or for example, when going from oil immersion medium into a watery specimen, the point spread function will blur just a few microns away from the cover slip, leading to a loss of both signal and resolution. This figure, taken from a paper by Stefan Hell, illustrates how much the signal drops off when you image away from the cover slip into unmatched refractive index media, an effect of spherical aberration. The cover slip is located at Z equals 4 microns, and at increasing depths, the graph shows the normalized signal intensity when imaging into dye solutions of differing refractive index, with a 1.46 NA oil immersion objective. You can see here how dramatically the signal drops off when you're imaging into a low refractive index media with this oil immersion objective. This figure illustrates that imaging with an oil immersion objective might not always be the best choice, depending on what the refractive index of your sample is. Furthermore, if the specimen, which includes the sample and the surrounding mounting media, is not of a uniform refractive index, the imaging will suffer from spherical aberration and lateral scattering. It should be noted that biological samples are highly scattering, because they're a collection of high refractive index molecules, such as lipids and proteins, in a low refractive index aqueous solution. Again, the aberrations and the light loss due to scattering will be worse the further from the cover slip you image, and the bigger the refractive index differences the light encounters. The best way to reduce these aberrations is to be very careful about the refractive index of your sample. Both spherical aberration and lateral scattering can be corrected or partially corrected by adjusting the refractive index of your sample, also known as clearing. Spherical aberration can also be corrected or partially corrected by choosing an objective lens that uses an immersion media closer to that of your sample, such as water or silicone oil. If you have live samples, you're not likely to be able to adjust the refractive index of the sample, but instead you can consider using a water or silicone oil objective. Which you use will be very sample dependent, so the best advice would be to test both. Adjusting the refractive index of your sample is possible when you're dealing with fixed cells and tissues. So how can we adjust the refractive index of the sample? As I said previously, both spherical aberration and lateral scattering can be corrected or partially corrected by adjusting the refractive index of your sample, also known as clearing. It's worth noting that most commonly used microscope mounting media can be considered simple immersion clearing agents. This figure, taken from a review on clearing by Richardson and Lichtman, shows that simple immersion clearing involves placing a biological sample in a high refractive index aqueous clearing solution for minutes to days to months, depending on the tissue size. During this time, the solution can be exchanged repeatedly if required until the refractive index of the sample equilibrates with the solution. This table shows some commercially available mounting media. I have no commercial interest, but I show this table because it has useful information for the purposes of this talk. People are often familiar with the advantages of using a commercial mounting media because of the antifade properties that they have. However, they also have the property of having a raised refractive index compared to that of water or your sample staining buffer. That means that if the sample is allowed to equilibrate properly with the mounting media, the refractive index of your sample will be raised. These mounting media are simple immersion clearing agents. Unfortunately, if you read the protocols, they often say no wash is necessary or add straight to sample on cover slip. And I assume that's because they're developed with single cells and cover slips in mind that can equilibrate in seconds or minutes. So let's consider mounting cells on a cover slip. If we now consider that the goal of using a mounting media is twofold, to provide an antifade reagent and to raise the refractive index of the sample to reduce spherical aberration caused by using an oil immersion objective, we can consider better the steps needed to clear the sample with this reagent properly. It can be as simple as taking off as much of the washing buffer as possible, adding a drop of mounting media and leaving to equilibrate for 5 minutes, and then ideally taking that off and replacing with new mounting media before mounting. Adjusting the refractive index of larger samples, such as this Drosophila embryo, might require a gradual series of washes to get the desired refractive index uniformly throughout the tissue. Many people have got into the habit of moving straight from an aqueous medium in which they're doing their staining into the chosen mounting medium. But to reiterate, you need to think about how to ensure that the sample itself ends up with a consistent refractive index throughout, that it has had the chance to equilibrate with the mounting media. Otherwise, you're just creating more surfaces that refract light between the mounting media and the sample. So here is an example of a series of washes that you might want to take a Drosophila embryo through before mounting in a glycerol-based mounting media. This brings me to the end of today's technical tea break. If we return to the original learning objectives, you're hopefully now familiar with the fact that refractive index describes how fast light travels through a material, and that, as described by Snell's law, it determines how much the path of light is bent or refracted when entering the material. I've discussed how refractive index affects resolution by relating it to the Abbe equation, and shown you how the refractive index of immersion media affects the angle of acceptance of light in the front lens of an objective, and thus the numerical aperture. Finally, I've discussed how refractive index affects your choices about the objective lens and mounting media you choose for your imaging experiment, on the basis that better matching of the refractive index of your sample to that of the objective immersion media reduces spherical aberrations in your imaging and so improves resolution and brightness at depth. Finally, here are the sources of the images and figures used in the talk, and in bold are some resources that I recommend if you're interested in exploring this topic further. So I hope you've had time for your cup of tea. Thank you for listening.